Hi friends, I'm back to teaching this method because my other videos had a buzz in the background. So if there's a glare, I think it's a better trade-off for the buzz. So I'm going to give you 2 examples of segment proofs and 2 examples of angle proofs, because it's just using the properties that you've already been doing. So the first one is on page 9 if you're in your printed notes. You can basically, they have to give you at least one clue before they ask you to prove something. So the only clue that they gave you is E is the midpoint. You have to pretend that it's all you know. You can't use anything below for a reason. The only things that can go here are definitions, postulates, theorems, and properties. So obviously the first one is given. Always check to make sure that it matches the given statement. But most proofs start with a given. And that's the first clue that you can use, and you have to build off of that. So for the next row, you can only look at row 1 and 2. You can only choose the reason based on these 2 ideas. So if all you know is that E is the midpoint of DF, why are we allowed to say that DE equals EF? Well, now you have to go back to your chapter 1, all of your definitions. That's simply the definition of midpoint. So let me refresh your midpoint, or your memory. A midpoint is a point which cuts a segment into 2 equal pieces. So if that says midpoint, that literally says 2 equal pieces. That's all they've used is the definition. So now same idea. You can only use the rows above to get the answer to this. So if you just look at row 2 and 3, that should look like something from your properties lesson. If you notice, this stayed the same, and this stayed the same. What got added into the equation was a plus DE here and a plus DE here. So you should have learned that adding the same thing to 2 sides of an equation is simply the addition property. Now when you did the lesson on properties, it was just letters like A plus B. This is just adding segments, so you have to find the same patterns, compare it to your properties. Okay, so now just look at row 3 and 4. The right side of the equation stayed the same. DEEF, DEEF. So what they did was they replaced this with this. Well, look at row 2. Oh wait, no I didn't. Not row 2. Why are you allowed to replace 2DE with DE? You didn't substitute, you just combined like terms. 1DE plus 1DE equals 2DE. So look for either the word combine like terms, or it might say simplify. Both of those are reasons that you're allowed to do that. Okay, step 5 is a tough one to spot. So if you're looking up through and looking for properties and looking to see if they substituted, when you get stuck, go ahead to the picture, because maybe it's obvious right in the picture. Sometimes you lose track of what you're looking at. So look where DE and EF are. DE is this, and EF is this. And DF is the entire thing. So this should trigger your memory all the way back to chapter 1, where we learned the segment addition postulate, where you add these 2 segment lengths together, and it should equal the length of the same thing. So that's the only reason that they could say that. Segment addition postulate. So you're going to have to recall all the definitions you learned in chapter 1 and 2, all the properties you learned in this chapter, all the postulates we've done, and all the theorems. You have to use everything. It builds on each other. So the last row, again, only look at the row above. See if you can figure it out. DF stayed the same. Let me clear this so you can see better. All right, so we're trying to figure out, why are they allowed to replace this with this? We'll look right here. If they state that these 2 things are equal, then that can be replaced. And what's the fancy word for replacing with something that it's equal to? Substitution. So again, you practice the properties so that now you can recognize them within a proof. It's like you're analyzing someone's work. Okay, next one. Every proof looks different, so you just have to practice and you'll get faster and better at recognizing them. Okay, all we know is that KL is congruent to LN. KL is right here, LN is right here. And it's right there, so we know this is the given. But look where LM, LN are. They're right here. So they never said these two are equal, they just said these two are equal and these two are equal. So now if you're comparing row 2 to row 1, look, all the letters stayed the same. Stayed the same, stayed the same. The only thing that changed is this symbol went away. This means segment AL, this means length, or KL, this means the length of KL. And then these little squiggles disappeared. So that means they're congruent, that means they're equal. So if they say two segments are congruent, but then they say their measures are equal, all they've used is the definition of congruence. Again, a vocab term you should have memorized in chapter 1. Congruence means two things have the same measure, and this says two things have the same measure. So without knowing your vocab, you're going to be really stuck. All right, next row. This is a property from the other day. If you look at it very closely, KL is right here, LM is right here. They're both equal to LN. So when two things are equal to the same thing, then they have to be equal to each other. That's called the transitive property. So hopefully you've practiced recognizing that, and now you can spot it more easily. And then the last row, only use the row above to get it. If the length of KL is equal to the length of LM, why are we allowed to say that L is the midpoint? That's because the definition of midpoint is a point which divides a segment into two equal parts. So here that they said those two parts are equal, therefore we can prove that because of the definition of midpoint. Okay, so that's the kind of thought process you have to go through. Let's do a couple about angles. And I'll just kind of help you see the patterns. All we know is that PQR is a right angle. PQR is right here. And that's all we know and all we can use. So we start with the given information. All right. If angle PQR is a right angle, why are we allowed to say that it equals 90? That's just by definition. The definition of a right angle is a 90. So if this is given, this must be true. So even basic terms like right angle can be used as definitions. All right, let's use, all right, here's that tricky one. These two statements don't really give us any clue about that, but go look at this picture. PQS is this little angle right here. Angles have to have 3 letters. The vertex has to be in the middle. This little symbol means angle. This M stands for the measure of it. So the measure of this orange angle. SQR is this little purple angle. And then PQR we already decided was the whole thing. So think back to chapter 1. When two smaller angles are added together to equal the larger angle, you have to remember that that was called the angle addition postulate, similar to the segment addition postulate. But it makes sense because the other one we were adding segments together. They were 2 letters. Here we're adding angles together. They're 3 letters. All right, so now analyze row 3 and row 4. Try to figure out what's different. PQS stayed the same. SQR stayed the same. Why are they allowed to replace PQR with 90? Because right here they said that PQR equals 90. And the fancy word for all of that is substitution. All right, and lastly, again, just use the row above. If 2 angles add up to 90, why are we allowed to say that they are complementary? Because the definition of complementary is 2 angles that add up to 90. Okay, that one's not too bad. Last one. All right, go look at where angle 2 and 3 are. Angle 2 is congruent to angle 3. That's this angle right here and this angle right here. Okay, so notice there was more to the given. Right here, 1 and 2 form a linear pair. 1 and 2 form a linear pair, but that's down here. So watch out for that. If there's two things in the given, they're probably both going to be in the proof. All right, so just look at these two rows though. If 2 and 3 are congruent, why are we allowed to say that their measures are equal? That's the definition of congruence. Again, congruence means two things have the same measure, and M stands for measure. Okay, just use 3 to answer line 4. If 1 and 2 form a linear pair, then why are they supplementary? You should know that the definition of linear pair is two angles that form a half circle, which means they're supplementary. And again, use the line above to answer row 5. If 1 and 2 are supplementary, how do we know that they add up to 180? Because the definition of supplementary is two angles that add up to 180. Okay. All right, this last one is not as simple. Compare row 5 and 6. That stayed the same, that stayed the same. Why are they allowed to replace 2 and 3? All the way back here on row 2, they said that 2 was equal to 3. If two things are equal, they can be substituted for each other. And lastly, back to our old trick. Just use the line above. If 1 and 3 add up to 180, then 1 and 3 are supplementary. That's still the definition of supplementary. So that can go both ways. Supplementary 180, 180 supplementary. They're both the definition. So the rule is, see if you can get it by just looking at the line above. If not, see if you can look up a little farther. And then lastly, if when in doubt, head to the picture, and it could be a postulate. So good luck with these proofs, and practice makes perfect.